Alright, so this is the formula that we have used and learned in the past few example, and now we are going to look at something which is a little bit more challenging than before. So alright, so what if the question wants us to expand this a plus b to a power of n, and we can see that the first term is no longer 1. And in this case here, we can actually make use of what we already know by factoring out a to a power of n, and what is leaving inside the bracket is just 1 plus b to a power of n, sorry, a plus b divided by a to a power of n. Alright, and in this case here, we are getting back exactly the same form as what we have been using in the past few example. So we can happily do the expansion by using this formula here. And just for simplicity, we are just going to substitute y equals to b over a for the following expansion. Alright, so let's just do it. A to the power of n multiplied by 1 plus, so we can refer back to the formula here, and 1. Okay, let's just write in the bracket first, and there's a reason for that. And then this is y plus n2 y to the power of 2 plus all the way um, down to y to the power of n. Alright, so the next step would be to bring the a to the power of n factor into the bracket. So we get a to the power of n plus n1 a to the power of n times y plus n2 a to the power of n times y squared plus all the way to a to the power of n times y to the power of n. Alright, and now it's time for us to put b over a in to replace y. So what we get here is n1 a to the power of n multiplied b over a plus n2 a to the power of n b over a square plus dot 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 to the final term, which is a to the power of n b divided by a to the power of n. So as we can see here, part of the a term is going to be cancelled by the b over a term, and so we get this final expression a to the power of n minus 1 b plus n2 a to the power of n minus 2 and b squared. And now we can actually roughly see the pattern of each and every term in the expression, and the last term would be just bn, and it's kind of symmetrical, which is what we are expecting at the beginning of the expansion, because we know that this is a symmetrical expression a plus b. So after the expansion, it should also be symmetrical, right? So we have an as the first term and bn b to the power of n as the final term. Alright, so let's represent the first term as t1, second term as t2, third term as t3. And so by doing this, we can represent tr plus 1, meaning the r plus 1 term in the expansion is equals to, when it is 1, you can see that b is of the order of 0 here, and a is of the order of n. And then for the second term, a is of the order of n minus 1 and b is of the order of 1. So for the r plus 1 term, we can actually deduce from this expansion here that is going to be, there will be a column nr like this one here, and a to the power of n minus r and b to the power of r, right? So we can see that for the first term, t is and r plus 1 equals to 1, so r equals to 0. So when r equals to 0, this is vanish, I mean it becomes 1. And then here is a to the power of n, and then n to n is just 1, so you get exactly a to the power of n, right? Okay, so and now we have learned something new, and let's apply it to solve this question here. So the questions want us to find the coefficient of x to the power of 3 in the expansion of x minus 3 over x cubed to the power of 7. So it's going to be a lot more easier if we just directly plug in the result that we just derived here, instead of trying to factor it out until you have this form here, then only you do the expansion. That's going to be a lot more troublesome. So let's just look at the r term in the expansion for this x minus 3 divided by x cubed to the power of 7. So in this case here, tr plus 1 is equals to, okay, here we have n equals to 7, so n is 7, and then for the r plus 1 term, this would be r, like what we see here, right? R plus 1, and then this is r, and then a will be to the of the power of n minus r, and b is going to be b, which is the second term, is going to be of the order of r. So then we get x to the power of 7 minus r, and b, which is minus 3 divided by s cubed to the power of r. So, and now we are just trying to simplify the expression into something which is easier to look at. So let's just factor out the number in this equation here, which is minus 3 to the power of r. And then what we left with is x to the power of 7 minus r minus 3r, right? So what we get is 7 minus 4r, right? And then we can say that the power of x is given by 7 minus 4r, and since we are only interested in knowing the coefficient for x to the power 3, so when x has the power of 3, then 7 minus 4r is equals to 3, right? And that can at least tell us which is the term that we really care of. So r will be equals to, you just swap the position, 7 minus 3 divided by 4 is equals to 1. So when r equals to 1, the coefficient is just going to be given by this term here, which is apparently the coefficient for x, right? So then the question is very obvious. I mean, the answer is very obvious, that you just need to substitute r equals to 1 into the expression minus 3 to the power of 1. So this would be equals to minus 21. And this would be the answer for this question here. Alright, that's all.